So we're gonna look at a couple strategies to estimate the solutions to a differential equation. So the first one is to use a slope field. So really it's kind of how it sounds like we're gonna find a bunch of different slopes and then look at the curve that it creates. We're gonna connect them to make a curve, okay? So we use this when we can't solve the differential equation using like our calculus skills. So we just plug in values for x and y to find the slope field. So this is one way. Okie doke. So first, we're going to use our old way. We're going to use the separation of variables to find the solution to the differential equation for dy over dx equals x. And then we're going to graph the slope field and compare it to what we have in our calculations. Okay. All right. So separation of variables. So we're going to do dy dx is equal to x. I'm going to separate and integrate. So dy is equal to x dx. And now it's time to integrate. All right. So now I have y is equal to 1/2 x squared plus c. Let's find some particular solutions. So if we have a curve, so remember this is our general solution. Okay. And we're going to find some particular solutions that go through the points 0, -1, 0, 0, 0, 1, and 0, 2. Okay. So at 0, -1, I'm going to go ahead and plug in 0 for x and -1 for y. So into my general solution, I get -1 is equal to 0 plus c. So c is equal to -1. So the particular solution would be y is equal to 1/2 x squared minus 1. All right, for 0, 0, I can see I get 0 is equal to c. So I'd get a particular solution of y is equal to 1/2 x squared plus 0, or 1/2 x squared. Okay. So for the x and my y, so when I plug in for y, I get 1 is equal to 0 plus c. So 1 is equal to c. So I get y is equal to 1/2 x squared plus 1. Okay, last one. There seems to be a pattern, but the y value is 2, and then 1/2 x squared, so 1/2 times 0 squared plus c is equal to c. So I get y is equal to 1/2 x squared plus 2. So these are the particular solutions that go through each one of the starting value points. So now let's take a look at our new technique to estimate using a slope field. Okay, so to create a slope field, I'm going to use my differential equation dy over dx is equal to x, and I'm literally going to plug in point values for x and y to get the slope. So I'm going to start with dy dx evaluated at -1, 0. And remember, we're plugging in for x, so my x value is -1. So the slope at -1, 0 would be -1. I graph that on my slope field, so I go to -1, 0, and oh, I did that wrong. -1, 0, and I look at where if I were to draw a long line, how would I draw the slope? I see that if my point is right here, I'd go up one to the left one and down one to the right one. So it would need to connect across like this. So I just look at, I'm aiming to connect those two dots right there. So I'm going to draw a little part of my line with a slope of -1, okay? If I do another, I'm just going to do another slope, dy over dx, evaluated at -1, 1. Again, the x value is -1, so the slope at -1, 1 is also 1. I'm going to be connecting to make a slope of -1, so something like this, okay? I know that any x value that has any ordered pair that has a -1 in it, because there's no y value to plug in, I'm just going to get a slope of -1, so I am going to draw those in now. Okay, so next up, we have dy over dx evaluated at -2, 0. So the x is -2. So at -2, 1, 2, 0, the slope is -2. So again, I would go up 2 to the right, to the left, sorry, 1, down 2, 1, 2, to the right 1. So I want to be connecting a line between these 2 points. So I'm going to just draw in a little curve that has a slope of -2, okay? Next, I'm going to do another value, but again, just like our last set of points, let's go to -2, 2. At -2, 2, because the x value is -2, the slope is going to be -2. So again, I'm going to be connecting between, see, 1, 2 to the right 1, and this up 2, up 2 to the left 1. So it's going to be like a pretty steep curve, like say like that. So anything that has a -2 in the x is going to have a slope of -2. All right, so dy over dx evaluated at 0, 0 would have a slope of 0. Okay, and dy, let's just do one more. dy dx evaluated at 0, 2 would still have a slope of 0. So I like these. These are great. These are very easy to graph. 0, slope of 0. Okay, dy over dx evaluated at 1, 0. So anything with an x equal to 1 is going to have a slope of 1. And anything evaluated with a 2 in the x is going to have a slope of 2. So all of my points with an x value of 1 is going to have a slope of 1. So I just connect between the two. I just imagine where the line is going to connect and draw in the slope. A slope of 1. A slope of 2, I go, really what I do is go down 1 to the left a half and up 1 to the right a half. So then I can connect those. That's a slope of 2. And then I make these parallel since they're all the same. Okay, so you can see how the curve, you can kind of see a curve forming here. So now let's say I want to find the solution, I want to estimate the solution given our slope field that goes to the point 0, -1. What I'm going to do is follow my tangent, my mini tangent lines, my slopes, okay? I'm going to, every time you can go in between the slopes at each one of the points, but you want to make sure that the slope at that x value is kind of parallel to the tangent next to it. Okay, so like this part of the graph is like parallel to this part of the graph here. Okay, and then we're going to just connect it up. It looks something like this. Again, this is an estimation. These are kind of tricky to draw. Okay, so what I see in the green graph is that this is the equation y is equal to 1/2 x squared minus 1. That's what it should be about, should represent the curve that we got when our graph goes through the point 0, -1. Okay, so in the particular solution for the for our curve that passes through 0, 0 would start at 0, 0. It's going to be like parabola. It's going to be a parabola. And this is when C is equal to 0. So when the C value is equal to 0. Okay? All right, let's do the next one. At 1, 0, sorry, at 0, 1, I can see the curve passes through. This is going to be when the C value is equal to 1. See, the C value equal to 1. Okay, and then our last curve that goes through 0, 2, I don't have any sketches to go through here, but this is when the C value is equal to 3, 2. Try that again, 2. All right, so a slope field just helps us sketch in what we think the solution to the differential equation is going to be. This is particularly used when we cannot solve our differential equation using like calculus. Okay, let's do another one. So, okay. On the diagram to the right, plot the slope field of the differential equation for dy over dx is equal to 2y. All right, so we're gonna plot in the slope field. We're gonna do like 2 of these and I'm gonna pause the video, okay? So I have dy dx, dy over dx is equal to 2y. That's what we're gonna be plugging into. So this one's kind of nice as well because we only have a y variable in our differential equation, so the only thing that's going to change our slope is if we change y values. So let's go ahead and evaluate dy over dx is equal to evaluated at any x and a y of -1, and we get 2 times -1, which gives us -2. So any point where y is equal to -1, we're going to have a slope of -2. Okay. So I'm going to go ahead and draw that in. -2. So I'm connecting between here and here. So -2 between here and here. And then I'm just going to make them kind of parallel. Okay, so let's do dy over dx evaluated at any x value, and then my y value of 0. So 2 comma 0 is equal to 0. So on the x-axis, the slope is going to be 0 at all points. And then let's do one more. Dy over dx evaluated at any x comma 1 is going to be 2 times 1, which is 2. So we're going to have a slope of 2, positive 2. So each one of these little tick marks represents a slope of positive 2 at each one of those points. Okay, I'm going to pause and draw on the rest of these. All right, so when we have our y is equal to 2, so y is equal to 2, the slope is 4, so it's very steep. And then when y is equal to -2, the slope is -4. So this, again, it's very steep in the negative direction. Now, in part B, we're going to estimate the curve, the solution curve, when it passes through the point 0, -1. Okay, so we're going to plot our point at 0, -1. And then we're going to follow the slopes of the tangent lines here. So I'm going to be like, this is a slope of -2. So we're going to try and keep it at a slope of -2. And then it decreases pretty quickly. Okay. And then up here, I can see that as we're getting close to y is equal to 0, the graph is going to level out because there is a horizontal, the tangent lines are 0, okay? So this is what our solution curve looks like. Eek. Okay, and again, it's an estimation. Let's actually solve this one because we can. So I'm going to start with dy dx is equal to 2y. To find the particular solution of a differential equation, we separate and integrate. So I separate. Dy is equal to 2x dx. Now integrate both sides. So I end up, oh, that's not a y. And it's not an x. This is 2y. Okay, so I get dy over y is equal to 2 dx. Okay, now I can integrate. So I end up with ln, absolute value of y, is equal to 2x. Remember to add c to one side. Okay, I raise both sides with a base of e. Okay, so I get the absolute value of y is equal to e to the 2x. Oops. This is e to the 2x times e to the c1. So I am going to drop my absolute value signs because I'm going to make my e to the c1 just a giant e, or giant c, okay? And remember that the c will absorb the plus or minus from the absolute value sign, so we don't have to worry about them right now, okay? So we get e c times e to the 2x, and you can put c2 or you can just put plain c. At this point, we're like at the last point of our c value, but we do know that it's different than our c1. Okay, so this is our general solution. Okay, and so what we need to do now is solve for our particular solution. By solving for c. So I am going to plug in the point that we plugged in, 0, comma, -1. So I get -1 is equal to c times e times to the 2 times 0. So that's e to the 1, or e to the 0, which is 1. So I get c is equal to 1. So my particular, c is equal to -1. So my particular solution is y is equal to negative e to the 2x. All right, let's see how that compares to my sketch. Okay, my slope field, this curve that I drew for you should represent, hey, it's actually not that bad. Negative e to the 2x. Yeah, it's like e to the 2x would be up here, okay? And then it was reflected over the over the x-axis. Woohoo! All right, let's go on to the next one then. Okay, I have one more for you, and then I have a present. Okay, so slope fields take a while to sketch, so I would like you guys to go ahead and sketch your slope field, and I'm going to pause this video. One thing, this slope field takes a really long time because you have an x and a y in your differential equation, so you actually have to evaluate the slope for every single point that we are going to plot over here, okay? And I need you to plot one more row. The y is equal to -1 point, so down here. Okay, and now I'm really gonna let you do this. Okay, I evaluated all of the points at -1 when x is equal to -1. So -1, comma 2, -1, comma 1, -1, comma 0, and -1, comma -1. And I got the slopes of -1 over 2, -2 over 1, undefined, and -2. So I'm going to graph those in at, so -1/2. So I'm going to connect between, I'm going up half to the right, to the left 1, and down half to the right 1 to make a slope of -1/2. So something like that, okay? And then a slope of, oops, I put that in the wrong spot, okay? The slope of -1/2, I'm going to connect right here. The slope of -2, it gets steeper. Okay, I'm connecting from here to here. All right, and then I'm going to erase my lines. Okay, a slope of undefined, since it's negative something over 0, I am going to write a vertical line, okay? And then a slope of -2 again. So it should match like that. Okay, now I'm gonna do this very systematically and start with my x values that have a 0. So 0, 2, 0, 1, 0, 0, and 0, -1. Even with my very systematic list, I ran out of room, so I put all the x values with a 2 at the top. Okay, so I'm going to sketch in each one of these slopes now. Okay, so I have a slope field that looks something like this. And then what I'm going to do now is find the particular solution. So I'm going to sketch in the particular solution for f of 0 is equal to 1. So on my slope field, I thought I added that. Okay, f of 0 is equal to 1. So we want the solution that goes through this point. So what I notice is that the slopes are getting less steep in the negative direction. So it's going to curve out like this. Okay, and I'm going to try and follow something like that. Okay, and then it's going to go undefined when it passes over the x-axis, because it looks like all of the points on the x-axis at y is equal to 0, the graph becomes undefined. So it's going to go undefined, zeroes out, and then goes back up like so. I know, it's kind of crazy. I had to double check my work. Okay, so I think on this side it's not quite so steep. Kind of does like this number. Okay, so what we're going to do is use our separate and integrate, because we can actually solve this one again, and then I'm going to show you your present. Okay, so our differential equation is dy over dx is equal to x minus 1 over y squared. Okay, time to separate and integrate. We have y squared dy is equal to x minus 1 dx. We will integrate now. We get at 1/3 y cubed, just checking my work, is equal to 1/2 x squared minus x plus c1. I always just label it c1 just in case. If nothing changes, it's fine, but then at least I showed good work. All right, we're going to solve for y, multiply both sides by 3. So I get y cubed is equal to 3/2 x squared minus 3x plus c2. And c2 is equal to 3 times c1. All right, and then we isolate y, giving us the cube root of 3 over 2 x squared minus 3x plus c2. All right, so now what we're going to do is look to see what our this is our general solution. Now let's find our particular solution. At 0, that passes through 0, 1. I think 0, 1. So we're going to do, 1 is equal to the cube root of 3/2 times 0 squared minus 3 times 0 plus c. All right, or c2. So I get 1 is equal to the cube root of c2. So I am going to cube both sides. So c2 is equal to 1. So I get the curve y is equal to the cube root of 3/2 x squared minus 3x plus 1. So this is our particular solution. Okay, the present. Slope fields by hand are very tedious to draw. So I found you a calculator. Okay, here is a slope field. Just kidding, let's try that again. Okay, here is a slope field calculator. And what I'm going to do is type in our original function, our differential equation, excuse me. So my computer is crazy. Okay, I have x minus 1 over y squared. And our slope field looks like our slope field. See, it's just a big version of our slope field. Okay, and then I'm going to test my solution. I'm going to be smart. I'm going to raise it to the 1/3 power because that's going to be easier for me. So 3/2, JK, 3/2 x squared minus 3x plus 1, all raised to the 1/3 power. Ta-da! Look how pretty that is. Okay, so when we can actually when we can actually solve the differential equation using calculus, we can test our solution in our slope field generator. Okay, that's it for today. I hope you enjoyed slope field.